I'm Ennemcien. Welcome to Photoelectric Effect. In simple language, photoelectric effect is the emission of electrons from metal surfaces when the surface is exposed to electromagnetic radiations. This was first discovered by the scientist Hallwash, Hallwach, Hallwash. It was purely just an example of serendipity. Serendipity means accidental discovery. I'm afraid I can't explain the origin of that word serendipity for lack of time. Anyway, later, Hertz and Lenard conducted an experiment to study photoelectric emission. You know that metals contain free electrons, but these electrons are free only to move inside the metal. They are not energetic enough to come out of the metal surface because of some restraining forces present known as surface barrier. It is quite simple because the atomic core near the surfaces, near the free surface of a metal will pull the electrons back to the metal body to prevent the emission. But there are several methods by which you can extract these electrons from the metal. One method is just to heat a metal. Then, at sufficient temperature, electrons will come out from the metal body. This process is known as thermionic emission. In earlier electronic gadgets, we had vacuum tubes where thermionic emission was the main fundamental process involved. Now these two tubes are now out of date. Now transistors took their place. Let us see what Lenard's observations or experiments. This is a photosensitive metal. Photosensitive metal means such metals eject or liberate electrons by irradiation of almost all radiations, provided having sufficient frequency. Potassium is a photosensitive metal. Potassium, cesium, etc. Suppose this be a potassium plate or a metal plate coated with potassium. And electromagnetic radiations are allowed to fall upon this plate. There is a plate connected to the positive plate of a battery. We call it collector. When radiations fall upon this potassium coating, electrons are emitted and these electrons are attracted by the positive collector plate. This constitutes a current. This is known as photoelectric current. Now this arrangement is enclosed in an evacuated chamber to avoid interference of gas molecules. Now, what are the observations? You know that if the potential difference between these two electrodes is V volt, then the maximum kinetic energy acquired by an electron is VQ, that is V into Q. Charge of electron is E, so it is V into E or EV. This kinetic energy, as this kinetic energy increases, how is this kinetic energy increased and what is the strength of photoelectric current and what on factors does it depend, etc., etc. by this experiment, they studied a lot of things. The main observations provided by this experiment are the following. One, the maximum kinetic energy with which electrons are emitted from the metal is found to be proportional to frequency of the incident radiation. The maximum kinetic energy of the emitted electrons. These electrons are specially known as photoelectrons. So maximum kinetic energy of photoelectrons is found to be proportional to frequency of the incident radiation. And at the same time, this maximum kinetic energy is independent of intensity of the radiation. This is one point. Next observation is the strength of photoelectric current that is related with the number of photoelectrons emitted by the metal. This number or strength of photoelectric current is found to be proportional to intensity of the incident radiation and is independent of the frequency of the radiation. So photoelectric current is affected only by intensity of radiation, not by frequency of radiation. Maximum kinetic energy is affected by frequency of the incident radiation and not by intensity of the radiation. Another observation was this: it is an instantaneous process. That is, there is no measurable time lag or time difference between incidence of the radiation and ejection of the electrons. Almost instantaneous process. Another point. A minimum frequency was observed for every photosensitive material below which photoelectrons are not emitted. This frequency is known as photoelectric threshold frequency. These are the major observations made by Hertz Lenard experiments. Observations are these. Now these observations remained unexplained until Albert Einstein provided a theory for which he was awarded Nobel Prize, and his well-known famous photoelectric equation thus emerged. You know, before Albert Einstein, Max Planck suggested that thermal radiations are emitted or absorbed in the form of quantum packets of energy. Albert Einstein accepted that proposal and applied it to photoelectric phenomena. He suggested that when light is incident upon a photosensitive material, light behaves like a material particle, or it assumes a particle nature, and it possessing a definite energy depending upon frequency of the radiation. According to Max Planck, energy possessed by a quantum of thermal radiation is E equals h nu, where h is called Planck's constant and nu is the frequency of the radiation. Einstein accepted that proposal or that theory without questioning it. it. But he named the the packet of energy or quantum of light energy as photon. Photon is having a peculiar behavior. Light behaves just like particles, that is photon nature, only at the time of birth and at the time of death. In between these two, light behaves as waves, because wave theory was well established by interference, diffraction, polarization, etc. But wave theory could not explain photoelectric effects. That is how Albert Einstein proposed his photon theory just to explain photoelectric emission. We will see the nature. According to his theory, a light radiation or an electromagnetic radiation of frequency nu is having a photon, is a stream of photons, and each photon possesses an energy h nu. When such a photon strikes an electron on the surface of the metal, this energy is transferred to the electron. A part of this energy is utilized to liberate the electron from its parent atom, or the atom in which the electron is revolving. And the rest of the energy is given as kinetic energy of the emitted electron. So the incident energy h nu is accepted by an electron in the metal, and a part of this energy is utilized just to get the electron liberated from its position, and the remaining electron, using the remaining electron, it comes out with that much kinetic energy. So applying the conservation of energy, we can write the equation like this. This is the energy of the incident photon, h nu. A part of this is utilized to liberate or to free the electron from the metal surface, that is phi 0. The remaining energy is converted into kinetic energy of the electron. So h nu must be equal to half mv square plus phi 0. This phi 0, that is the minimum energy required or utilized to free the electron from the, or to liberate the electron from the metal. This is known as photoelectric work function. So this is the basic equation of Albert Einstein. Suppose if the incident radiation is having a frequency nu 0, the electron is not coming out but only just liberated from the metal. That is, the radiation of frequency nu 0 is just able to liberate the electron but not able to supply it sufficient kinetic energy to come out of the metal. Then we can write that h nu 0, h nu, in the place of h nu 0, h nu, you put h nu 0 equals kinetic energy is now 0 plus phi 0, or h nu 0 is phi 0. This means that nu 0 is the minimum frequency required to liberate the electron, but not sufficient enough to supply the kinetic energy for emission. Now you put this phi 0 back into this equation, then you get h nu equals half mv square plus h nu 0, or kinetic energy, maximum kinetic energy of the emitted photoelectron, half mv square equals h nu minus h nu 0 or h into nu minus nu 0. This is the well-known photoelectric equation of Albert Einstein. The derivation is quite simple. Now we have a lot of things to discuss about this photoelectric effect, graphical study, and so on. We will see in the coming postings. Please subscribe and view all the earlier postings. Thank you.